is we're hoping to kind of come back to, this is what we were ending with last Friday. We were starting to do calculations involving hydronium and hydroxide and how they're related to each other. And what we're going to do today, we're going to try our best to finish out the chapter. If we don't, we'll take some off for Monday as well. But since it's been a week, I wanted to take a couple of example problems here at the start to get us back into what calculations we were doing at the end of Friday, just to kind of refresh ourselves of where we were last week. So let's start with this problem here. And it's a pair deck problem, so I'll, let you get the participation points, but let's work on it together here. So the question is this: given our concentrations of hydroxide ion in each solution, calculate the concentration of hydronium in the solution and determine if it's acidic, basic, or neutral. So the equation that we have to remember is that hydronium concentration is equal to Kw, so 1 times 10 to the negative 14th, divided by the hydroxide concentration. So for number 1 here, 1 times 10 to the negative 14th over 1.9 times 10 to the negative 8. And if you remember, one of the notes that I left you with on Friday was specifically about scientific notation in your calculator. Making sure that you're using that scientific notation correctly so that you don't get weird answers. So 1 times 10 to the negative 14th divided by 1.9 times 10 to the negative 8. Make sure you're using your scientific notation button for that bottom exponent especially. Otherwise, make sure that you put that denominator in parentheses so that it does not accidentally multiply your answer by the exponent instead of dividing. Regardless, 5.3 times 10 to the negative 7 molar is the concentration of the hydronium. Now, to answer this second question, is it acidic, basic, or neutral? We have to compare. Is the value that we just calculated bigger or smaller than the hydroxide? Which number is larger? This one or this one? So the trick here is looking at the exponents. Since the exponents are negative, the smaller the negative exponent is, the bigger the number is. So negative 7 is bigger than negative 8. So hydronium is higher in concentration. And if I have more acid than base in the water is going to be acidic. For the second problem, 1 times 10 to the negative 14 divided by 0.0310 This time we don't have to worry about scientific notation because our denominator isn't in scientific notation. We get 3.23 times 10 to the negative 13th. That's our concentration of hydronium in this case. So again, we have to compare what is this number compared to this number, which one is bigger? And in this case, we've got something to the negative 13 here, so we've got 12 zeros in front of that 3. Or we've got 0.03, so that would, in scientific notation, that'd be negative second. Negative second is far better than negative 13. So our hydroxide is bigger than our hydronium. The base is stronger than the acid. So we call that basic. All right, any questions with this example? All right, make sure you get your responses into Pear Deck so that you get your participation point there. All right, let's do some more. Now we have an example of where we're trying to do calculations of pH from concentrations of hydronium or hydroxide. Now, the key trick here is, again, recognizing our definitions. pH is equal to the opposite of the log of hydronium concentration. Well, in this case, we don't have hydronium concentration, we have hydroxide concentration. So if this is my concentration of hydroxide, in order to find the concentration of hydronium, I'm going to need to do the same kind of calculation that we just did. 1 times 10 to the negative 14 divided by 5.0 times 10 to the negative 7. So 1 times 10 to the negative 14th divided by 5 times 10 to the negative 7th. 2 sig figs here, 2.0 times 10 to the negative 8 more. Find pH, I take the opposite of the log of the hydronium. So 2.0 times 10 to the negative 8. So the logarithm of 2 times 10 to the negative 8 is going to give me negative 7.70. The opposite of that would be positive 7.70. Just a rule on the sig figs here. Not gonna be too relentless on this one, but just so you know, the general rule of thumb for how many decimal places that you carry out in a pH calculation is based upon the number of digits in the concentration. Every digit in the concentration becomes a decimal point on the pH. So my concentration had 2 digits. My pH has 2 decimal places. That's the general rule of thumb for pH calculations. Haven't talked about it yet. Not going to see it a whole lot. I don't think mastering is too terribly picky about it. But that's the general rule of thumb to use. So whatever your concentration is, that number of digits is the number of decimal places that you put in your pH value. Now, to answer the question about acidity, well, we could go 2 ways with this. The pH should tell us pretty directly. We know that pH is above 7 are basic, pH is below 7 are acidic. So this is above 7. We could have gone that way. Now, based on what we just did, the problem before, we can also answer it that way as well. My hydronium was known to the -8. My hydroxide to the -7. The hydroxide concentration is bigger. So the water is more basic than it is acidic. So we could have concluded it was basic just off of the concentrations. Wouldn't necessarily have to go to pH. Although it is easy. Because you can just look at it in relation to 7. 7 is neutral, above that is basic, below that is acidic. All right, questions? All right, with these, we're going to run off of kind of a similar principle. All of these are strong. The HCl is a strong acid, sodium hydroxide is a strong base, the nitric acid is a strong acid. So what that tells us is that since it is strong and we know that it breaks apart completely, the concentration given is not just the concentration of the acid, it's also the concentration of either the hydronium or the hydroxide, depending upon what it is. So that tells us that the hydronium concentration in this case is 0.00085 molar. That tells us that the hydroxide concentration in this one is 0.010 molar. That tells us that the hydronium concentration in this one is 1.0 molar. With that in mind, try to figure out the pHs for these 3 solutions. And just remember, pH is the opposite of the log for the concentration of hydronium. So in 2 of these 3 cases, I just need to take the logarithm. In the middle case, I need to turn it into hydronium concentration first, then take the logarithm. Give you a few minutes, try to work through this as best you can, and then we'll come back together and talk about it. Okay, a couple of things I noticed as I was walking around. So, first of all, a lot of you are making a common mistake with number 1 and number 3. And it makes sense because we did it every other time. If we're calculating pH, we need the hydronium concentration. So if we already have the hydronium concentration, we don't need to do anything further. We just need to take that number and find the logarithm of it. And that's our pH value. What I saw some of you doing was you were doing the divide by 1 times 10 to the negative 14th divided by that number calculation. And that would be great if it was hydroxide and we we're trying to find hydronium. But we already have the hydronium. You need to do that calculation with the second one because it is hydroxide, not hydronium. So for number 1, all we need to do is take the opposite of the log of that concentration. And if we do that, 0.00085, logarithm of that's negative 3.07, turn the negative into positive, positive 3.07. Would be the pH. And that's all that you would need to do. And same thing for number 3. I just need to take the opposite of the logarithm of 1.0. What you find is that the logarithm of 1.0 is 0. So the pH of that particular nitric acid solution would be 0.00. Now, again, that's a theoretical value. In practice, you take that, you put a pH probe in 1 molar nitric acid, it's probably going to come out in 0.4, 0.5, or something like that. That gets into a lot more complicated how water actually reacts with acids than we're willing to get into here. For the middle, here's where we had to do that calculation first. 1 times 10 to the negative 14th divided by 0.010 would give me 1 times 10 to the negative 12th. And then the opposite of the log of that would give us a pH of 12. So once you get into it, the calculations here aren't terribly difficult. There's just a lot of different places where you can kind of make silly mistakes. And for the most part, if I was looking around, that's where I was seeing most of you making mistakes, was just in little tiny silly things that once I corrected you, you were able to kind of do it on your own pretty well. Questions here? Okay. Now, what if I told you that there is actually multiple ways to solve some of these problems that we are doing? And in fact, in some ways, some of the calculations can actually be made a little bit easier. And one of the ways that we can do some of that easier stuff is through something called pOH. Now, pOH is another logarithmic scale. It actually runs in the exact opposite direction of the pH scale. So 0 on the pOH scale means that we have something that's really basic. 14 on the pOH scale means that we have something really acidic. pOH of 7, again, means neutral. Calculation-wise, it's the same calculation as pH, only we're using hydroxide concentration instead of hydronium concentration. Now, here's where it gets easier. pH and pOH can add together to give us 14. So if we go back to those problems that we just did, we could have actually solved the middle problem without doing that calculation to find the hydroxide concentration. What we could have done instead is use the hydroxide concentration to find pOH. And since pH and pOH have to add together to get 14, you could have come up with the pOH through kind of like a back door. You'd taken the logarithm of that 0.01, you'd have got 2. pH plus 2 is 14, so pH must be 12. That kind of math is a little bit easier to do. So what we're leading to is that there are 4 calculations, 4 different kinds of things that we can determine about a solution from a pH standpoint. We can look at the pH, we can look at the pOH, we can look at the hydronium concentration, we can look at the hydroxide concentration. And all 4 of those quantities are actually related to each other mathematically. So if I wanted to find the pH of a solution from the hydroxide concentration, I could go around this square and do a couple of calculations to get me there. And so this calculation square shows me the kinds of calculations that I can do to connect any corner of the square to the other. Now, the only calculation that is missing, the one that we haven't done yet, are these 2 on the bottom sides. Something called an anti-log. The anti-log calculation would allow us to take a pH or a pOH and turn it into a hydronium or a hydroxide concentration by basically taking the anti-log. So a logarithm puts it on that particular scale. The anti-log would take it off of that scale and put it back in the decimal form for us. And on your calculator, anti-log and log usually share a button. So if you look at your logarithm button on your calculator, there's usually written in small print above it, 10 to the x. That 10 to the x button is your anti-log button. And so it's the opposite function. So just like we use logarithm to turn hydronium into pH, we can use anti-log to turn pH into hydronium. We can basically reverse the process. And so that's what this looks like right here. So if I wanted to do a calculation like this, where I was trying to evaluate the pH of a soil sample and figure out what the hydronium concentration was, all that I would have to do is, since I'm given a pH value, I can stick that pH value right there. 10 to the negative pH will give me hydronium. So on my calculator, because it's a scientific calculator, it doesn't have stored functions of any kind. I have to do this in reverse. So negative 6.2, then anti-log. It's going to give me to 2 digits, 6.3 times 10 to the negative 7th molar for my hydronium. And just remember, your sig fig rule reverses itself here. So when we were finding pHs, we looked at the number of digits in the concentration and turned that into a number of decimal places. Here we do the opposite. The number of decimal places in my pH becomes the number of digits in my concentration. So I have 2 decimal places in the pH. That's why I rounded to 2 digits in the concentration. Because believe me, the calculator gives you dozens more. So let's take a look at another example here. In ecology, if the pH of water in a lake falls below 4.5 due to acid rain or runoff or a variety of other reasons, the lake can be considered dead because basically nothing can live in a pH that low. Question is, what is the pH of a lake that has a hydroxide concentration of 3.2 times 10 to the negative 9th molar? Secondary question, would this lake be considered dead? Now, to answer that question, ultimately what we are doing is we are being asked to connect hydroxide concentration to pH. And if we look at our calculation box here, we can see that there are 2 ways that we can go about doing it. One way would be to turn the hydroxide into hydronium, and we've done that calculation a number of times. That's where we divide 1 times 10 to the negative 14th by the hydroxide concentration, and then turn the hydronium concentration into pH by taking the logarithm. That's one pathway. The other pathway would be I turn the hydroxide concentration into pOH, and then I use the relationship between pH and pOH to find the pH. Now, personally, I like this second option better because I don't have to deal with all that scientific notation nonsense and trying to divide everything out and not getting into any potential issues. Plus, it's a lot easier to add and subtract than it is to multiply and divide. So that's the direction I would go personally. But with that calculation square, we can see that you could go another direction that way as well. So I'm going to calculate pOH. pOH is equal to the opposite of the log of the hydroxide concentration, which would be the opposite of the log of 3.2 times 10 to the negative 9. So the log of 3.2 times 10 to the negative 9th is 8.49. There's my pOH. The second calculation is that pH plus pOH equal 14. So pH plus 8.49 equal 14. I can do a little bit of algebra. pH is going to be 14 minus 8.49, 5.51. The answer to the secondary question, is the lake dead? Well, the pH is above 4.5, so the answer is no. So I hope you can see why I favor this particular method. Especially if you have any kind of mental math skills whatsoever with adding small numbers together. It's not a far leap to figure out what you need to add to this to get to 14. And that makes the second calculation all that much more easy. Just remember what the first calculation would be otherwise. 1 times 10 to the negative 14th divided by 3.2 times 10 to the negative 9th, and then taking that result and taking the logarithm of it to get the pH. I think this is just a little bit easier. But again, that's one person's opinion. You can take that for what it is. If you like the other way, because we did so many examples the other way, that's perfectly okay. Just understand what you're doing with it in the end. All right, any questions with this example here? All right, we've got a couple minutes left. Let's go ahead and at least try to finish out the top row of this pair deck question. And so what I want you to do is using that calculation square, and you can go about this any way that you want. For that top row, the purple row, try to determine the values of A, B, and C. Keeping in mind the relationships that exist. And so what I'm going to do is I'm going to pair deck should still be open. So if the pH is 1.31, figure out the other 3 values. Figure out the pOH, figure out the hydronium, figure out the hydroxide. Since we're starting to run short on time here, I'm gonna kind of show you how I would approach it, and then kind of leave it to you to take it and go. And so since I have the pH, the route that I would be going is I would use the pOH to find, or excuse me, the pH to find the pOH. So I would just subtract the pH from 14. That'd give me the pOH. And then I would be using the anti-log functions to go up to the hydronium and the hydroxide concentration. Now, you could choose to go completely around the square. You could do that. But the reason I favor the other approach is because if you look at my results here, the math is pretty simple this way. I have to do a subtraction, and I have to do a single function to find the hydronium and a single function to find the hydroxide. And I don't have to do division in any kind of way for any of them. So that's the approach I would take. And so when we come back on Monday we have just the tiniest little bit of this chapter left. We have just the tiniest little bit. We need to talk about how do you measure pH, and we need to talk about a particular type of pH resistant solution called a buffer. And honestly, we'll do part 2 of this as well, just as review, just to kind of get us in the right mood for the rest of the calculations. Your homework this weekend is these kinds of calculations. Using that calculation box and just converting from one to the other, to the other, to the other. And giving you some practice with that. But after we finish this out on Friday, or excuse me, on Monday, we are going to get into gases. Gases are our last unit of study in this entire book for the entire semester. So once we get through that, and we'll take one more exam, I'll take another mini exam just over this stuff and gases. Once we get through those things, we're going to have 2, maybe 3 sessions to get ready for the final exam. So that's kind of the plan for the rest of the semester. If you got this in, you're free to go. Otherwise, try to get it in before you do so. Have a great weekend.